Howdy, and welcome to the Instrumentation and Automation Symposium. I want to tell you that as a Texas A&M #1 screwball, I have worked for many years to support this symposium and to put on these technical sessions. And I want to tell you that I and the rest of the volunteers are so grateful to you for your attendance today. With COVID, the beginning of the year, late notice, and all the other challenges that have been presented to you this year, thank you for your attendance. Today I'm going to be talking about high integrity protective systems and issues beyond it as a safety instrumented system. Now, my background with regard to HIPS is over 20 years. I wrote one of my very first technical papers presented at the Loss Prevention Symposium on overpressure protective systems, and it won that year's Loss Prevention Best Paper Award. Since then, I've written a chapter for the Instrument Engineer's Handbook. I have served as a consultant for the Welding Research Council Bulletin on how to do the risk assessment for high integrity protective systems. I have a lot of papers on this subject, and I don't want to repeat that information. And so here is a list of the papers that are available on my website at SIS-TECH.com. So if you look at these, I will not be talking to you today about how to assign a safety integrity level to your HIPS, how to design it for any particular application, such as designing it for handling reactive cases, which can be very complicated because you're trying to predict what the reaction is doing and what path it's on. I won't be talking about using HIPS for wellhead protection, and that's where you detect that the pressure in the pipeline is coming up to a point where it could begin to threaten the pipeline, and you simply shut down the wellhead pump prior to overpressuring the pipeline. I am also not going to talk about how to network high integrity protection systems. So let's say you have loss of cooling water, or loss of power, some other loss of utilities case that causes a big load, and so you have multiple safety instrumented systems or HIPS that need to take action to prevent overloading the flare system. So today, really what I'm going to focus on is what are all of the considerations that you should be thinking about when you're designing a HIPS that doesn't really have anything to do so much with the HIPS simply as a safety instrumented system that needs to comply with all of the various codes and practices that apply to vessel overpressure protection, as well as AICHE 61511. There are a lot of ways that we minimize overpressure events. First is that we could design the process to be inherently safe. And of course, that means that we're specifying a maximum allowable working pressure of that equipment that is actually greater than the maximum pressure that the process can achieve. So essentially, overpressure can't happen, do it. You can also have a reduction in your overpressure events by simply improving your process control. We see a lot of overpressure events occurring during startup periods where things are unstable, and by slowing the ramp rate of the temperature that the operator takes the process to, perhaps we prevent those pressure swings that happens through that fast startup that results in a bumpy startup. We can also look at how we improve our operator response to alarms and how we can lower our abnormal operating rate by analyzing those periods of pressure deviation and looking to see what we can do in the control algorithm or the operator procedures to simply slow that down, reduce the number of demands that we're placing on later layers of protection. And of course, as we go through the layers of protection, one of the papers that I listed was, just how fast do my systems have to be? And the better we're able to use control and the better we're able to use our operator, the fewer significant changes to the process we'll have to make. So the operator brings it back down. The control system brings it back down. The HIPS shuts it down. the pressure relief valve, vents it out. So the next layers are layers that have a significant effect on productivity. So the next way that we can minimize overpressure events is by use of a pressure relief valve. And many practitioners feel very strongly that this is the inherently safer choice. This is what is actually mandated by the ASME pressure vessel code, unless you meet all of the exceptions included in that code, and they are specifically laid out, the forms of proof that you have to have. But it is considered the inherently safer choice because it's a simple mechanical device that operates by virtue of what the process is doing. The force is coming from the upset process, so I don't need any other utilities. So loss of utilities doesn't affect it, neither does fire. If I have a fire, the pressure relief valve will work as specified. But a pressure relief valve can be an impractical choice for some scenarios, especially when there is a source problem. A reaction, I mentioned my paper on reactive processes earlier. An exotherm can produce pressure faster than a pressure relief valve can lift it. You can also have a hot spot occur in a localized area, which results in excess heating. Remember that MAWP is a function of the metal temperature, so as we heat that side up, the MAWP can begin to degrade, leading to a blowout in that hot spot area. This is something that a pressure relief valve cannot mitigate at all, so we have to be able to detect when these potential hot spots are occurring and shut down. You can also get into polymers, deposits, salts, solids, things that can deposit in the entry header of the pressure relief valve due to splashing or high level events. You can also have, during the relief, some of these materials being carried up into the entry header and out, leading to deposition and potentially blockage of the outlet path for the gas. So these are cases where there's a problem with the source of pressure itself. You can also have pressure relief valves really be impractical due to a transfer problem. When we open a pressure relief valve, we're transferring the pressure from one place to another, Where is that other? And what's the risk of that source receiving this pressure? So you might have a case where the pressure relief valve is not relieving to a safe location. And so you need to ensure that you have a very low likelihood that you'll need to open that pressure relief valve. You may determine that your flare or your disposal system is not sized for a new hazard scenario that you've identified. Your flare disposal system might not be designed for the hazard scenario. In that case, you may have identified a scenario that you didn't understand before. It could be that debottlenecking activities you've done that have increased the production rate have also increased the size of the venting case, and the system that you currently have will not accept that load in combination perhaps with other loads or by itself. So we want to take action and prevent that pressure relief valve from having to lift. You may be in a remote location where there's really no practical vent location. So you've got a remote wellhead, whether that's onshore or offshore, where what would you do? Spew oil, spew gas into the local terrain? Your most obvious choice of stopping the problem is, so why not just detect that the event is occurring, that you've got that high pressure coming, and shut the pump down and then not have anything spill out in the ocean or spill across the ground. Another means that is the focus of this paper is the high integrity protective system. This system is essentially a specialized type of SIS It's not outside the SIS, it's a type of SIS, and you can have more than one of those protecting a process. The hips should be completely independent of the process control system, much in the same way that your pressure relief valve is independent of the process control system. The SIS detects that some variable is going askew. Predominantly it's pressure, but it can also be temperature, flow, level, or some analytical measurement. And then the SIS takes action on the process to isolate that pressure source and prevent the pressure from going higher. The use of a HIPS is often justified based on cost, technical feasibility, and regulatory pressure. Now, cost is something that a lot of process safety professionals really don't like us to talk about, but it's a reality. If I'm looking at a remote facility and in order to have a pressure relief valve be my primary means of protecting this pipeline, I have to build a giant flare. It doesn't make cost sense when what I can do is put in a highly reliable high integrity protective system that can detect very close to that pump that there's a problem and shut the pump off. Cost practically always has to be a consideration. It shouldn't be the only consideration, and we should remember that a pressure relief valve is the inherently safer choice. It's the one your people really don't have to think that much about. And I'll be giving you some more comparisons between pressure relief valve choices and SIS choices or HIPS choices in just a moment. Now, the high integrity protective system is often introduced after the process design package is complete. And so the HIPS is a bolt-on instrumentation like a lot of other instrumentation, but it does have a significant impact on the process operation. And we need to ensure that the procedures and the rest of the process design package understands this new planned cause of process isolation and also the knock-on effects that can happen when the trip happens, and then what do we do to recover from this overpressure event. So the accepted rationale is that HIPS can provide protection similar to or better than a pressure relief valve. And that's for scenarios that involve process deviations. Clearly, a high integrity protective system is not going to be effective in fire cases because we're essentially bottling up the vessel and heating it. So HIPS do not address fire cases, but they do address those process deviation driven cases. Primary concern that I and many other practitioners have is that a lot of people stop with the risk reduction. This can provide me with equivalent risk reduction, and they don't think about all of the complexities that go along with designing, implementing, and long-term operation and maintenance of a HIPS system. Where do the differences lie? When you look at a PRV, it's kind of like a fidget spinner. It's a simple mechanical device. I put it between my fingers and I spin it around and I fidget with it. And a HIPS is more like a Rubik's Cube. I can fidget with it, but in order for that fidgeting to achieve the goal of the Rubik's Cube, I've got to work something in 3 dimensions, and I've got to keep up with patterns, and the challenge is how fast can I do it. So the HIPS is a lot more complicated than our pressure relief valve. The much greater design complexity. There's also engineering challenges with implementing the HIPS, installation and operation maintenance practices as well. So these are the things that I'm going to spend the rest of the presentation talking to you about. The pressure relief device design is an intimate part of the process design scope. There's not a process engineer that doesn't automatically draw a vessel with a pressure relief valve. The calculations for those pressure relief valves are actually taught at the undergraduate level. AICHE's SASH program provides an educational materials to undergraduate chemical engineering programs across the country. So people coming straight out of college know these calculations. The calculations are very well defined. Even when we have complex cases like reactive cases or multi-phase fluids, API and dyers through AICHE have provided well-vetted calculations on how to do those things. There's not a lot of question about whether we have the right kind of competency to do these calculations. We do. We have a lot of support within our community. As far as the design, the pressure relief valve does not take any direct action on the process control system. So the operator and the process control system are working within their normal domain. The pressure gets high, the pressure relief valve lifts, you have a release of that pressure, and then it resets. And within that envelope, the operator recovers. So an overpressured blip is just a blip. You write it out. There's a low likelihood that that lift propagates into a major deviation in other pieces of equipment. Your pressure relief valve is sized for your largest case, and it handles all of the smaller cases. So you don't have to worry about understanding every source of pressure that you might have. Where with the hips, we could be isolating a vessel, and if we have not isolated all the pressure sources to it, and we still have one of those sources coming, we could get an overpressure of the vessel, and that would not happen with a pressure relief valve because it does not care where the pressure source derives from. In the engineering and in the installation, the specification is typically limited to just a few options in terms of the type pressure relief valve that goes in a particular service. As I said, the calculations are already very well known. The pressure relief valve will open within milliseconds without any special design. The failure mechanisms of the pressure relief valve are well known, and the things that we can do, such as purges or rupture disc, are also well known for those applications where those are needed. So reliability is highly predictable as long as you are working to ensure that that inlet header is good and that the pressure relief valve internals are in good shape. So you are pulling it out, you are inspecting it, you are cleaning it, you're testing it. And there's limited ways to install it. Once you've got your connection to the vessel, you can't install it upside down, you can't install it sideways, you can install it the way it's designed. So it's a lot harder for there to be a systematic error. As long as you've got that isolation valve between it and the process open, it's pretty much installed and ready to go. For operation and maintenance, it is not acceptable to operate a process without a functional pressure relief valve, so you never have to worry about compensating measures for doing that. It has a long, useful life and very little obsolescence issues. So once you've bought a pressure relief valve, as long as you're not getting erosion, corrosion, deposition, or cycling of the pressure relief valve so that you're damaging the seat, you've got a long-term investment that can sit out there. No obsolescence. No one's going to come in and say that you need to upgrade anything on that pressure relief valve. Maintenance is prescribed by practice, and many times it's done by specialized third parties, so you don't have to worry about having the resources on site to take care of that pressure relief valve. You pull it, you send it off to be tested. Failure tracking is easy because all the data comes in as a snapshot. You know, based on the demands placed on those pressure relief valves at the test stand, how many passed, how many failed, what services were the failed ones in, what services were the passed ones in, and you do your investigation. So there's only success and failure data. There's no constant stream of data as we can get from our high integrity protective systems. So for HIPS on the process operation, it takes direct action on your process. So it's looking at your process and shutting things. Well, what's going on upstream and downstream? Well, upstream, I had a pressure source, so somebody's putting pressure here. What happens to that, and how am I managing that? Downstream, there was something that was getting feed, and now it's at no flow. So something downstream is experiencing a no flow event. So when we look at our process hazards analysis, the majority of our scenarios kick off from no flow. We blocked a discharge, we blocked a suction of something, and that leads to other hazard scenarios. So there's an immediate impact, not only on your process operation, but those that are sending materials to this process and those that are receiving materials from this process. So there's just a very high likelihood that the HIPs are going to trigger other events within the process that you need to ensure that the overall HIPS design and overall control system design is managed. So when this HIPS takes action, where do we report that to? What does the DCS do when it gets that trip indication? And so that's making sure that you're cleaning up your full trip so that it's nice, neat, soft landing. The design complexity, well, a HIPS design can require specialized competency, especially when you're doing things in reactive services and networking flare load HIPS. Understanding what happens when you're in a high demand mode service is also critical, because as I've already mentioned, this really impacts your process operation. So if you've had a history of flaring events from your process, yes, putting in a HIPS will reduce the amount of flaring. It's just going to cause a lot of process operational problems because you're going to experience more disruption of this particular process. And so you really need to dig down and look at that process control and look at your operator procedures to see how you can reduce the number of demands. Make your startup process smoother so that you don't have those pressure excursions. The reliability of HIPS is very dependent on the device selection, the architecture, the installation, and the site maintenance practices. How well do you take care of your purges, your heat tracing? How clean is your instrument air? How frequently are you doing inspection and maintenance? HIPS requires a lot more attention. There's a lot of diverse applications of HIPS. There's no mandated SIL for any of those. So if you're an independent assessor, you can't look at a HIPS and say, well, this house must be SIL 3. So the SIL could be SIL 1, SIL 2, or SIL 3, depending on how much you are depending on that HIPS to resolve the overall risk of that scenario. There's no standards HIPS design for SIL 1, SIL 2, or SIL 3, so you can't look at a PNID and recognize a HIPS. And this is quite different from the pressure relief valve. I could look at the PNID and go, whoa, there's my pressure relief valve. This is just going to appear as the other instrumentation does on the PNID. So you don't have that level of visibility of what is protecting my process from overpressure. You actually need to have someone who understands how to do a HIPS design analysis, especially if you're looking at flare load mitigation. It's amazing how many times I've consulted with people on where the common cause factors go in a network design. Hint, hint, they're all at the top of the tree. Even then, this tree is limited to the random hardware failures of the SIS. And so many things that can happen at a site long term are not taken into account in these calculations. So one of the key differences between a pressure relief valve and a HIPS is that a pressure relief valve is just one gadget. And there's a lot of components to a HIPS, each one of which has a wide range of performance capability. Are you on the upper end or the lower end of that? It depends on your operation and maintenance practices. So there's at least 3 times as many devices in a HIPS for the same level of protection that one pressure relief valve is providing to you. It is a complex system of integrated equipment, and its response time is dependent on the system design and installation. There are lots of devices to track and maintain across the life of the equipment. A lot of this equipment includes programmable electronics. There are the cybersecurity issues associated with that programmable electronics, but there's also a high rate of obsolescence. And so where the pressure relief valve, it's out there, as long as it's mechanically good, it's out there. You'll be changing out transmitters as they obsolete software. You'll have to update systems as patches come in. And so there's a much more care and feeding that has to happen. And then a lot of those components also have short useful life. So within your life of this process, within this capital investment, you're going to be replacing components of the hips multiple times, where you buy a pressure relief valve generally once. Installation and maintenance practices can be much more complicated if we have network protection. So if you have combined all of your hips that are protecting your flare system into one logic solver, then that one logic solver failure results in the entire network being lost. Where a conventional design, you have a one pressure relief valve per vessel, and so if one pressure relief valve fails, that's only a problem in that one vessel. It's not a problem in all the other vessels. With a network system, you're creating the potential that one failure could result in overpressure events across the site. So a much more catastrophic event than would be predicted by any of the individual PHAs and LOPAs done on those process units. So do keep that in mind. There are numerous ways to bypass the hips, and a lot of them are not obvious. There is external hardware that can be added, internal software configurations. We can build manual forces into the program where they are intentionally built, and all you got to do is put on the force, or you can use manual forces within any of the software tools today, and none of this is visible to operations and maintenance. So systematic issues are more prevalent with hips than they can be with pressure relief valves, and that's why we have to have a strong bypass maintenance program, as well as documented compensating measures for how we're going to be safe while that system is undergoing online repair. Remember earlier I said pressure relief valves are not repaired online. We will repair many components of the hips online. So how are you maintaining risk reduction? How do you shut down that process should an abnormal event unfortunately occur while you're doing maintenance? And on that maintenance effort, a lot of the offline testing is done by third parties, much like the pressure relief valve testing. But the care and feeding of a HIPS is an ongoing effort. So your on-site personnel will have to be trained on how to do those inspections and maintenance of those devices, how to diagnose, troubleshoot, repair, and correct a problem. When a pressure relief valve is pretty much an install it and don't think about it anymore. So there's a lot more data coming in for your HIPS system potentially. Data is collected at different times due to diagnostic fault reports. It may be coming in because of inspection, finding issues with connections or conduit or bent tubing, you know, things that are showing that they're degraded but they haven't failed, as well as failure data. You'll still get that snapshot data at turnaround. You'll also be getting this big load of other data that you'll need to parse through, and you need to ensure that you've got a high data quality, or you're getting a lot of data that you can't do anything with. So data quality is key, and it's one of the issues that we emphasize at the Instrument Reliability Network. You know, so in summary, when you're looking at your risk reduction, you may be looking at a teeter-totter between a pressure relief valve and a HIPS, but you need to recognize that the pressure relief valve is the inherently safer choice, but sometimes it's not feasible or practical. HIPS take a lot more work than simply saying, well, I need SIL 1, 2, or 3. There are a lot of things that need to be done long term, and so it's a choice that you can make, and you can make safely, and you can achieve the risk reduction and the safe operation that you desire, as long as you remember all of these other things that need to be done in the design, installation, operation, and maintenance of those systems, so that you do achieve that equivalent risk reduction long term, not just on paper, but in the real world. Thank you very much for listening to my presentation. I hope that you enjoyed it, and now I'll take questions. Thank you.